A mineral, as you know, has this definition. It is a naturally occurring inorganic solid with a definite chemical composition and a repeating crystal structure. You need to make sure you know what each of these parts of the definition mean. We went over them yesterday. I am not going to go over them today. How do minerals form? Who can tell me what you know about how minerals form? There's two primary ways that minerals form. The two primary ways that minerals form, one is by evaporation. And we all know around here we have what's called hard water. The water has a lot of minerals in it. As the water evaporates, it leaves salts and minerals and a very hard, white, crusty stuff behind. Those are the minerals. And the minerals that are left behind are a number of different things, but this is how minerals form. This says a gypsum rose. I don't know if you've ever seen one of these. We'll see one of these when you go to the museum. It actually really does look like little petals of a rose, the way it crystallizes. We'll talk about gypsum a little bit more. This right here says water containing minerals. Seawater, or really any water, has a lot of stuff dissolved in it. As that water evaporates, like if a pond dries up, or a lot of our lakes right now, lakes and ponds are lower than normal, and you can see up on the shore kind of where the water level used to be, and you can see that kind of bathtub ring of stuff left over. And then if that gets made into sedimentary rock or whatever, those sediments get preserved and you'll actually have minerals. You can imagine if seawater evaporates, there's a lot of salts. The Great Salt Lake in Utah, there's a tremendous amount of salt there because the water flows in, but it doesn't really flow out. So over probably thousands or hundreds of thousands or millions of years, tremendous salt buildup there. And they actually mine that salt in the Great Salt Lake and use it to, for the salt we buy at the grocery store. So evaporation of water is one of the primary ways that minerals form. The other way that minerals form is volcanic activity, and as somebody mentioned, hot water solutions. This says here, minerals can form on the surface through, oops, that's the other one. They can form beneath the surface when dissolved elements and compounds leave a hot water solution or when magma cools and hardens. And so the reason the water is hot is because it was heated by the magma. So hot water underground, and it's hot because of magma, and so that might come out of solution. You can also have the magma itself as it cools, cooling magma. And again, like anything, once you melt it, it separates out a little bit because the different parts of the rock have different melting points, and so you'll get little stuff kind of, it precipitates, but it comes out of solution. Here we have pure silver can crystallize in veins. The textbook talked about veins. They look like veins and arteries, but it's in little channels in the rock, and that's where it forms as the magma and lava or the hot water solutions cool. But then when people mine for silver and gold and all those other metals, they go down into the rock and they'll find a vein, and they keep mining down and digging up all the precious metals or minerals that that they're looking for. Questions about that? The fact that there's a lot of mining here in the Rocky Mountains, gold mine, silver mine, all that kind of stuff, what does that tell you about the way the Rocky Mountains formed? Tell you something about their formation if there's a lot of veins of minerals and precious metals? On the recording. So the two main ways that minerals form, evaporation, which is on the surface of the earth, and volcanic activity, and this is happening below the surface in the crust. And they asked you a question, I believe, on the worksheet. What does the rate it cools have to do with the size of the crystals? And the answer is? If it cools slowly, the crystals are bigger, just like we talked about in the granite, and it makes sense if it has a longer time, it builds bigger crystals. And so you'll see huge crystals if it cooled very slowly. Any other questions about mineral formation? All right, we move on then to, these are the characteristics of minerals. And these are going to be very helpful as we look at our minerals tomorrow. The main characteristics to identify minerals are color, streak, luster, density, hardness with an extra S, crystal systems, cleavage, and fracture. So I will go over each one of these. Some of these, as you can tell, are quite obvious, and others are a little bit tricky. So let's start with the first one, color. These, actually, we're going to do the first two, color and streak. Now, again, these are pictures cut straight out of the textbook. If you want to follow along in a textbook, you can. Color, again, pretty obvious type of thing. We looked at the quartz. Quartz is usually clear, sometimes has a little bit of color from impurities. And then, of course, you know that this is gold, has that characteristic yellowish shiny color. And then these are two types of what you might call fool's gold. This is the most common one around here. Anyone know what fool's gold? Pyrite, iron pyrite. And you can see, even though it has a similar color, it's a little bit more greenish. And when we will look at a sample of pyrite tomorrow. We will not look at a sample of gold, a little too expensive to have in our labs kits. But the crystal structure is a little bit different too. And then this is another one. It's called chalcopyrite, something like that. Chalcopyrite. I hadn't heard of it before, but it's another pyrite. It's another mineral. But you can see the color is different. So color, again, pretty obvious. You look at the color. The only problem with identifying them that way is you might look at it and say, oh, I think it's green. I think it's tan. There might be that issue. The next one is a little bit tricky. The next one, I don't like the way the textbook defines this one. It's called streak. But the way the textbook defines it is something like the color of the powder, which is really strange. But what streak is you take the mineral and you scratch it on a white ceramic tile. Yeah, this is the definition of streak. And then what color the streak is the mineral's streak. Now that might seem obvious, but it's a really interesting thing. Sometimes you'll have something like this one right here, the malachite. It is a little bit bluish, but what color is its streak? Green. So this one, the streak is green. Usually it's very similar to the color of the mineral, but sometimes it's quite different. Hematite, so it's kind of reddish. What's this one? Galena. We will have a sample of galena. And it's got it looks almost like a pencil. And so scratch on white ceramic tile. The color of that scratch equals its streak. And some of them, as you do the streak test, will have very little streak. Some of them will have a very dark streak. So that is streak. And again, in the textbook, it has a definition I don't really like. I believe it calls it the color of the powder or something really strange like that. But basically what they are referring to is as you do this, part of it kind of comes off onto there. I will do this definition on the quiz because when we do the lab, that's how we will do it. All right? No, don't worry about the types of minerals, but when you do your tests tomorrow, you will be doing a streak test. For the 5 or 6 minerals for each one, you'll look at the streak, the color, the crystals, all those things, and then you'll go to a chart, and from that chart, try to figure out what mineral it is. Okay? Are we ready for the next two? All right, the next The next characteristics, luster and density. Luster we already talked about today. Luster is kind of interesting because it has, I think, luster is basically the shininess or the sparkliness, but there are a number of terms for luster that you might not be familiar with. So luster, shininess, right? You might want to write down these terms, but the luster could be metallic, or it could be glassy. Quartz, of course, would have a glassy luster. Mica would have a glassy luster. The metals, of course, obviously would have a metallic. You guys know what metallic is. This one's a little odd. This is waxy, greasy, or pearly, which is a little strange, but basically what they're saying here is it doesn't have a lot of sparkliness. So luster isn't just going to be yes, no. You're going to have these different words to look at it. Does it have that kind of waxy, pearly look to it? Now, this one's a little bit weird. This one says earthy, which again, a little bit of a strange word. But do you think this one's going to be very sparkly? No, probably not. Earthy. And that one says it's hematite. That's usually kind of a darker color. This should be separate from the color. This one, silky. Do you think silky is going to be very shiny? No. And then this one, submetallic or dull. Is this one very shiny? No, submetallic means below metallic or less than metallic or dull. And yeah. And so what you're seeing is the three on the top are a little bit more sparkly, and then these ones are a little bit less sparkly. But write down those words. You will be using those words as you look at the rocks tomorrow. Some of them, again, are very easy. If it's metallic or glassy, piece of cake. Some of the other ones are a little bit trickier. But as you look at them, it will help you eliminate. Well, if it's not metallic, then it cannot be this list. And when you look at the list tomorrow, one of them is a whole thing, dark colored minerals are on this page. Metallic minerals are on this page. And so it helps you figure out which group it's in. Everybody good with luster? All right. Now, density. What is density? Yeah, it's mass divided by volume. But tell me, what is density? What does it mean? How do you know if something's more dense? How close the molecules are together? How heavy it is? What's that? Not as many air pockets. If it has a lot of air pockets, is it dense? No. If you had a styrofoam ball and a golf ball of the exact same size, which one is more dense? The golf ball, of course. Generally, every single person knows pretty distinctly. If I said which one's more dense, you know which one's more dense. How do you calculate density? That gets a little trickier. It is mass divided by volume. Excellent. D equals M divided by V. Now, how do you find the mass of a rock? How do you find the mass of a rock? Okay, guys. Mass. If you wanted to measure the mass of, you weigh it. Thank you. You put it on the scale. The mass would generally be in grams. And we will use the 3-beam balance. Okay. And somebody says, well, then how do you do volume? There are two ways you could do volume. How do you normally calculate volume? Anybody? Volume? How do we get volume? Yes? Ah, yes. He has come up with the way that we will do it in this class. So volume, if you're in math class and you have a really nice square thing, like a nice cube, you know, you could do like length times width times height and get volume. However, our samples are not going to be nice shapes. They're going to be lumpy rocks. So what we are going to do, let's move these things over. No, move over. The way we are going to determine density, and I'll remind you of this tomorrow, we are going to take a graduated cylinder of water, yeah, and see how much it displaces. And so what you want to do is fill the water up to a known amount, like 100 milliliters. Then you put the rock in, it'll make it go up, and then you say, okay, its volume is whatever. And then you'll have a little calculator, you'll divide mass by volume. It'll be grams per milliliter. Or it could be kilograms per liter, but to simplify it for you, we'll just do grams per milliliter. Okay? Everybody good with that? Yes? So the definition of density, you could just say the definition of density is mass divided by volume. And if I asked you to define it in words, somebody else said the amount of mass in a given space and somebody else said how closely packed the molecules are. So if you were to answer this on a test or a quiz and I said define it in your own words, then describe it to me so I know what you're saying. You could say a golf ball is more dense than a styrofoam ball because it's more solid. There's more. It's heavier for the same size. Okay? So describe it so it makes sense to you so I understand. And being able to say mass divided by volume is also good. All right, everybody good with density? Wonderful. Got luster and density. Let's move on to our next characteristics. Now hardness is interesting because obviously it's pretty easy to describe, okay, yeah, how hard it is. Is it harder than something else? Okay, but how do we describe that in the lab? Did anyone remember reading about the hardness scale? Excellent. Did everybody get that? But you're exactly right. So hardness, we use what's called the Mohs hardness scale. And we're going to go through it right here. And when you do this part in the lab, you have to use the textbook. You have to use the textbook because you'll know. Now, everybody knows what is the hardest mineral, the hardest substance is diamond. Guess what? Diamond is a 10 on the Mohs hardness scale. Nothing can scratch diamond. Okay? Well, can it scratch itself? They use a diamond blade to cut it. Excellent. Right, but that's, okay, so you could break it, right? But that's not scratching it. So smashing it is one thing, but scratching it, putting a scratch on a smooth surface is different. So diamond is a 10. Now the softest mineral is something called talc. Has anyone ever heard of talc? Has anyone ever heard of talc before they read this chapter? Like talcum powder? It's really soft. This is so soft, you could break it down with your fingers. It says here, the softest known mineral, talc flakes when scratched by a fingernail. Okay? And you could just powder it down with your fingernails. And then the other one, which is maybe a little bit more familiar to some of us, I mentioned it yesterday. No, not yet there. Gypsum. This we might know also as sheetrock or drywall. that building material, it's got like a little layer of cardboard and it's got that white stuff in the middle, sheetrock or gypsum board. But the gypsum board or the sheetrock is a mineral. It's a mineral they mine out of the ground to make this building material. And it's generally white. And you see right here it says a fingernail can scratch it. So that's how soft it is. Talc and gypsum both say, sometimes it gets a little bit tricky here. This says flakes. So this one actually falls apart. The talc actually falls apart when you crumble it with your fingers. The gypsum, you can scratch it. All right, so it's kind of a subtle difference, but it is a difference. So you'll see that a lot on this scale. The talc breaks apart with the fingernail. The gypsum can be scratched. Then you have calcite, fluorite, apatite, feldspar. I know, isn't that funny? Feldspar cannot be scratched by a steel knife. It can be scratched, but it can scratch window glass. So as was mentioned, each one of these is given a hardness based on what can scratch it or what it can scratch. So as you're doing the lab, you will have your textbook out in front of you using this. The calcite, a fingernail cannot scratch it. A copper penny can. Fluorite, a steel knife can easily scratch it. Apatite, a steel knife can scratch it. Can't be scratched by a steel knife, but can scratch glass. And then here we go. Here's another one that's very familiar to us, quartz. Actually, going back to feldspar for a minute, feldspar is generally pink and obvious, and it's oftentimes in granite. So that's why you might recognize feldspar. Quartz can scratch steel and hard glass easily. So quartz, which is a very common mineral, especially around here, which has a very distinctive and a very distinctive crystal, is something that we use. Not only you identify it, but you can use it to identify the hardness of other things. And then you have topaz, conundrum, and diamond. But those really are the ones that you will see a lot. Gypsum, quartz, and what was the other one in there? Yeah, well, diamond. So anyways, that is how you figure out the hardness. You have to have some of those other things to identify. Questions about hardness? Okay. All right, next, crystal structure. Now, we talked about this already. I'm not going to spend a lot of time on it. Again, when we do our classification tomorrow of the minerals, you will have pictures and you can identify the minerals based on what the crystals look like. So crystal structure, and basically when we're talking about the crystal structure, you're talking about the shape or the number of faces. And so you have something here. This is magnetite, and look, it looks very much like a cube. You can have a cubic crystal. You can have this one, which is a little bit hard to see. It has kind of a hexagon and is in kind of long channels like this. Huh, what mineral does that look like? Quartz. Yeah. Right. So it says in the definition, it says a repeating crystal structure. But what you'll see, like the sample of quartz that I showed you, there's a bunch of them. And so you'll see this not just one time in the mineral, but a bunch of times. And quartz has a very distinctive hexagonal structure, and then usually it's kind of pointed on one end. But this one's cubic. This one, tetrahedron. This one's more rectangular. This one looks kind of like a rhombus. But basically what you're seeing in each of these is a distinctive crystal shape. And as you look at your mineral samples, some of them will very clearly have a crystal structure and some of them will be more difficult. All right, our final two categories, fracture and cleavage. Okay, so this is, of course, how the mineral breaks, which is sometimes quite distinctive. Oops. And I know you talked about this last week. If it has perfect cleavage, what does it look like when it breaks? Flat, right? Perfectly flat. And this has, we will see samples of mica. Mica is actually a relatively common mineral around here. There's mica, which is generally clear, and there's also, we always called it black mica. It actually has a different name, which I have to look up. But it says here, mica cleaves into thin, flat sheets that are almost transparent, and it's very, very distinctive, right? Now, don't get confused. Some people say the hardness of mica is really low because you can break it apart. But you don't look at if you can break it apart. You look at if you could scratch this surface. Okay? Mica is very distinctive. It flakes into little flakes like that. It's mica. So cleavage is when it breaks in flat sheets or flat faces. Okay, and then if it has fracture, it's going to be different because fracture, think about how glass breaks. Fracture, it's going to leave kind of more of a circular. Think about when you break flint or obsidian and it makes those little, to make blades, and it makes that sharp little edge. This says it looks like the surface of a seashell, but it's going to have kind of the opposite of cleavage. It's going to have that little rounded, sharp edge. Everybody good with fracture and cleavage? Biotite mica. What's that? All right, next. The final thing, and we will actually not be doing this one just because it doesn't work so much with the samples I have, but special properties. There's two really awesome special properties that minerals might have. One of them is fluorescence. They glow under black light or ultraviolet light. And many people who collect rocks, which they do here in Colorado, will have these collections of rocks, and the rocks, and we'll actually see this at the museum too. The rocks look really like dumpy and boring and brown and dirty, and then you put the black light on them, and they are blue and green and red and really beautiful fluorescent bright colors under the black light. And again, unfortunately, I don't have a black light, and I don't think we have any of the fluorescing minerals, although I'll see what I can do to find that. But that is obviously a very unique special property that if it has that, that's pretty easy. The other special property is magnetism. This is an easy one. Guess what? If it's magnetic, guess which mineral it is? Magnetite. Oh, magnetic properties. There are a couple other ones. We'll have to see if we have some halite or calcite. Calcite is really cool because when you look through it, because of the angular thing, it actually bends the light. Oh yeah, and if it's if it reacts with acids.